Lectures on single phase induction motors. So, we have seen that a single phase induction motor having only one winding on the stator will have only running torque, there cannot be any starting torque. And then we develop the equivalent circuit of the motor when it runs on single winding. Of course, to get the equivalent circuit, we brought an imaginary coil whose magnetic axis is perpendicular to the main winding and assume that current to be 0 while developing the equivalent circuit and hence the expression of the torque. But now the question is, you cannot have a motor which is not having any starting torque. Of course, physically if you run, it will start in any direction you like, but that is not a very technical answer. One should not operate a motor like that. Therefore, to incorporate starting torque, what now you have to do is that the rotor is there like this cage induction motor rotor, and here is a main winding as usual. And now I connect a physical coil, it is now no imagination, nothing like that. This is physical coil, auxiliary winding coil, auxiliary coil. Okay. And this coil I will call coil A. Okay. And it is now physically present, both the coils are present. So, and these two coils will be eventually connected in parallel across a single phase supply. Okay. Now, the question is suppose and everything now I will be dealing with the assumption that machine is stationary or S equal to 1. At that instant what is happening if you switch on the supply? So, at standstill condition, because I want to investigate how starting torque can be incorporated in a single phase induction motor with the help of another winding which is called auxiliary winding or sometimes called starting winding. So, these two coils will be eventually connected in parallel and across a common single phase supply like this V. Therefore, I mean this current is I m, current drawn by main winding, and current drawn by auxiliary winding is I a. Now, if the impedances of these two coils seen by the supply at S equal to 1 are different, then there will be a time phase difference between these two currents, and let that current be denoted by I m and I a. When you connect it across the supply V at standstill condition, machine is not allowed to rotate. In that case, once again these two currents can be broken up into a positive sequence current. I m can be written as I m 1, these are all phasors, plus I m 2, and we have done several times this, and the auxiliary winding current, this I m I a are unbalanced two phase current can be thought of, and this can be written as I a 1 plus I a 2, but I a 1 is the positive sequence is nothing but j I m 1 and this is minus j I m 2, this will be the thing. And this time I a is not equal to 0, that is what I want to say. It is a physical coil, it is carrying a current. So, that is there. Now, from this equation what I am planning to do first is express I m 1 and I m 2 in terms of IM and IA, that is what IM and IA. That is what we will be planning. So, two equations are there, that is not at all a problem. In fact, if you call this to be equation 1, this to be equation 2, I mean I am doing this way, it can be done several ways. I will multiply the second equation 2 with j both sides. So, that it will be j I bar a is equal to minus I bar m 1 j j minus, and this will be j j minus and minus plus I bar m 2. Let this be called equation 3, and this two equation I will now use to get this thing results. For example, if you add 1 plus 3, add 1 plus 3, if you add, it will be 2 I bar m 2, 2 I bar m 2 from the right hand side, and this will be equal to I m bar plus j I bar a. It will be like this. Similarly, if you subtract 1 and 3, 1 minus 3 if you do, then I m 2 will go off and it will be 2 I bar m 1, this minus this is equal to I m bar minus j I bar a. This is the thing we have got. Why it is necessary, it will be just clear why this knowledge or the expressing I m 1 and I m 2 will be necessary. I will tell you that. But now, let us see what this means. See, this equation is I am rewriting here. So, 2 I bar m 2 is equal to I bar m plus j I bar a and 2 I bar m 1 is equal to I m bar minus j I bar a, correct. So, suppose this is the voltage phasor, this is the voltage phasor, is that clear? So, there will be current taken by auxiliary winding and there will be current taken by main winding. Suppose this is the current of the main winding, and suppose this current is the I bar a. Suppose the impedance of auxiliary winding is such that it is leading. Therefore, this angle will be theta a, the power factor angle of auxiliary winding, and this angle will be theta m, the power factor angle of this. Let the total angle be theta a plus theta m. Suppose theta I m and I a, angle between them is theta. So, I will just avoid writing this V. What I will simply tell that so we know, suppose the angle between I m and I a phasors is theta, and let me only draw these two currents. So, this is suppose I m, voltage phasor I am not drawing, and this is suppose I a, and the angle between them is theta, like this. V was here, for example, in the earlier one. Now, we know that 2 I bar m 2 is equal to I m plus j I bar a. So, to get this negative sequence component of I main winding current, I have to add to I m j I a. Where is j I a? JIA is so IA is here, JIA will be right angles to this will be JIA, is not JI bar A. Is that clear? Therefore, you add this is suppose IA parallel to this I have to this is 90 degree. So, this is J I bar A, and I am telling this will be this then will be 2 I bar M 2, and similarly 2 I bar M 1 is equal to I m minus J I bar A. So, I m is already there, J I A bar is this. So, minus of J I A bar I have to add to I bar m. So, it will be this way, this is minus J I bar A, and if these two are added, then this will give you the value of 2 I bar M 1. Is that clear? That is what you will get. Okay. So, I have got now two triangles. Recall that this angle, the angle between, this is the direction of I bar m. So, this is theta, this is 90, this whole angle is 180. Therefore, this angle must be 90 minus theta, 90 minus theta must be this angle. Now, I will go to the properties of triangle. Consider this triangle, that is suppose the sides are A, B, C are the sides of the triangle, then any side square, for example, C square is equal to A square plus B square minus 2 AB and cosine of the angle between these two. This is the standard thing. So, I will use that. So, so this side square must be equal to this side square plus this side square, this is I bar m. So, this square is equal to this square plus this square minus 2 into this into cosine 90. So, I can write, but this time I am writing only the magnitude, no phasor business, sides of a triangle, their lengths. So, I will be getting 2 I m 2 its magnitude squared, without bar means magnitude I am meaning, this must be equal to I m squared, this length square plus this length square, do not put minus I a square, length I a square its magnitude, then minus of 2 I m I a into cosine of the angle between these two. So, angle between these two is 90 minus theta. So, cosine 90 minus theta, I will write it better. So, cosine 90 minus theta. So, I will get 2 I m 2 squared is equal to I m squared plus I a square, and this is minus 2 I m I a sin theta. So, this is one equation, important equation. So, I have been able to express I m 2 in terms of I m I a, as I was telling, and in terms of the angle between I m and I a. Similarly, you come to this triangle, this lower triangle comprising of sides I m, 2 I m 1 and minus j I a, these sides. So, here once again this is 90 minus theta, this whole angle is 180. Therefore, this angle must be 90 plus theta. Not. And here once again you see it is equal to this side square, that red side square, its magnitude 2 Im1 squared. This must be equal to Im square, the length of this side square, plus the length of this side square. This is once again Ia square, the length of this sides Ia square, then minus of 2 Im Ia, 2 Im Ia into cosine of the angle between these two sides, and that is 90 plus theta. So, it is cosine 90 plus theta, or it will be 2 Im1 squared is equal to Im squared plus Ia square, and cosine 90 plus theta is minus sin theta. So, this will be plus 2 Im Ia sin theta. This is the other equation. So, this is one equation and this is another equation. Okay. And these two equations I will be using to find out the torque in the machine. Torque means starting torque, because I will not allow S to change to any value, standstill condition, whether there will be starting torque or not. In fact, when I will do that, it will be necessary to know this one. If you subtract, this is suppose 3, this is suppose equation 4 and this is suppose equation 5. So, if you do 5 minus 1, in fact, their difference will be of importance, and I could do it later, but anyway, since it is in the same paper. So, minus 2 Im square minus 2 Im2 square, this minus this, if you do, these two terms cancels and you will be left with 4 Im Ia sin theta. So, this will be the thing. Okay. This result will be actually utilized, say 6 here, 6. Now, how to find out the expression of the torque? Now, remember that this is the thing I am discussing about. This is the machine, Ia, Im is there. Ia, Im I have broken up into positive sequence current and negative sequence current. Therefore, they are going to be two rotating field, depending upon Im1, Ia1 and Im2, Ia2 in the opposite direction. Each one of them has per phase equivalent circuit. What will be that per phase equivalent circuit? It will be something like R1, X1, is not, and Xm and R2 dashed, X2 dashed, per phase equivalent circuit of that balanced machine which is excited by Im1 and Ia1. What will be, and this current I am telling it is I bar A at S equal to 1, there is no R2 dashed by 2S, it is a balanced 2 phase machine. Per phase impedance is R2 dashed. Similarly, this Im2 and Ia2 will also have the same exactly same equivalent circuit, because slip is 1 x m and this is R2 dashed X2 dashed, and this current is the main winding current. I am sorry, this is I m, I bar M 1, and this current is I bar M 2. S equal to 1 in both the case, nothing like R2 dashed by 2 minus S, no, S equal to 1. So, this is the scenario. When I am telling it is ZA, I am telling that if you apply a voltage to this, what is the impedance seen by the main winding. Similarly, for the auxiliary winding ZA, I will manipulate these resistances. Now, in this case, if you leave it like that, it looks like ZA and Zm will be same, is not? But that is what I am telling. Here, what I will do in all this analysis, I have assumed I have connected something in series with the auxiliary winding, some external impedance apart from its own impedance here. So, that will make that thing change, that you keep in mind. But what I am telling, since S equal to 1, whatever impedance is being shown to the supply by the machine at S equal to 1, that we take into account to describe ZA Zm. And another thing I have assumed, the number of turns of this main winding is Nm and that of the auxiliary winding is also Nm, I have assumed. So, that the reflected R2 dash is same. Are you getting? This point is somewhat important, because R2 dash is what with respect to auxiliary winding, R2 dash is what with respect to main winding. In any case, this is the scenario, and I have assumed Na equal to Nm. What is Nm? Number of turns of the main winding. Then it is taking Ia, it is taking Im. Now, I will assume, since S equal to 1, this Xm is, because you are only try to guess approximately, I will not guess, try to get an approximate expression of starting torque. So, I will assume this Xm is much higher than this parallel R2 dashed plus Jx2 dashed, whatever it is. Are you getting? So, that as if that current is the current flowing through the air gap resistances, which represents torque. In other words, whatever I have talked right now, I will tell that the starting torque can be approximated to this Im1, this current Im1 is as if flowing through this R2 dashed because of this assumption. Okay. I will not distinguish between Im1 and whatever you call this parallel, because R2 dash X2 dash, in this case I know pretty well it cannot be high, there is no R2 dash by S, Xm is high. So, estimation of the torque will demand that that T starting therefore can be simply written as 2 Im1 square into R2 dashed in synchronous watt, that is all, per phase into 2. And from physical reasons I know the negative sequence is in the opposite direction, that is why I have put the mind, because that rotating field will rotate in the opposite direction. So, I will write 2 I m2 squared into R2 dashed in synchronous watt. and if you like, this will be equal to 1 by 2 pi n s synchronous speed into the same thing here. Therefore, this is the expression of the starting torque of the single phase induction motor having two coils, main and auxiliary winding, and whose impedances are not same, that is R1 X1. Here of course, I have written that. What I am trying to tell, in the auxiliary winding I have connected something. So, here as if I have connected something here, that is that auxiliary winding business I have connected like that. So, this is the thing. So, if that be the case, then you know the torque produced will be equal to, in synchronous watt only I will do, T starting then will be equal to R2 dashed into like this. This will be the expression of the torque. So, difference of Im square minus Im2 square is coming. So, this will be then equal to, in this previous case recall that I have got this one 2 Im2 square minus 2 Imn square is 4 Im Ia sin theta. So, from this I can write Im1 square minus Im2 square is equal to Im Ia into sin theta. No 2 is missing, na? Hopefully. So, this will then be equal to, I will write 2 R2 dashed into Im1 square minus Im2 square, and this one is nothing but Im Ia sin theta. So, it will be equal to 2 R2 dashed Im Ia sin theta. This is the expression of the starting torque. See, one thing is clear, that your machine is like this. This is main winding, this is your auxiliary winding. If the power factor angle of both these coils are same, then theta will be 0. Theta is after all the angle between Im and Ia. So, this equation tells you that the starting torque of the induction motor can be created provided your, if this is your supply, if this is your I bar m, and if this is your I bar a in phase, then theta will be 0 and no starting torque can be provided. Therefore, to have a starting torque, you must phase split the stator impedance of the auxiliary winding with respect to the primary winding. So, we will continue with this in the next class. Thank you.